Okay, so what we're going to do is we're going to predict flow using Darcy's law. So that's our objective. Okay, and Darcy's law is really pretty straightforward. So let's say we've got ourselves an aquifer. Okay, and this aquifer has got sand in it. So I'll use a bunch of dots. That's going to represent sand. Okay, and then above that aquifer, we're going to have a confining layer. And a lot of times, whenever we see clay, you can use these sort of things, and that is going to be clay. And that's going to be our confining layer. And so what we want to do is we want to predict what the flow is through the sand. And so we can define the flow through the sand using Darcy's law. So we're going to make this a little bit more complicated. We're going to give it a width, and we'll call that width W. And we'll give the aquifer a height B. Okay, and then we'll extend our clay over here. And so what we have here is we're flowing from 2 points. So let's say that we're going to start over here, and we will call this point 1. And we're going to flow over to point 2. And so we're going to have, in this example, 2 different water elevations. And just to make sure that I don't mix it up with the clay, I'm going to give my water the color green. And so I'm going to flow from these 2 locations, and typically we use this little triangle to illustrate that is the water elevation. So we're going to go from H1 over to H2. And we are going to go over a distance x. So we'll say that this over here, this is going to be x2, and that's going to be x1. Okay, so now Darcy's law is flow is equal to negative multiplied by the permeability, which is the ability to transmit flow, multiplied by H1 minus H2 divided by X1 minus X2. Okay, and we are going to need to multiply this by an area, and our area is just the width multiplied by, or the height multiplied by the width. So our height is B, our width is W. Okay, and so now all we need are some values in order to figure out what this flow is. So we'll say that a permeability is going to be 10 to the minus 2 centimeters per second. And that is just by convention. Many people have come to understand permeability in terms of centimeters per second. But in our example, we are doing feet, and so we're going to have to do a conversion. So you've got 2.54 centimeters, 1 inch, and 12 inches in a foot. And you can go online and do the conversions and so forth, but I've managed to memorize those, and maybe you have as well. And so it's an easy conversion. You do the math on this, and this is just 3.28 times 10 to the minus 4, and that's feet per second. Okay, and so now what we're going to do is we need some additional values. So for this example, we're going to say that H1 is equal to 100 feet, H2 is equal to 80 feet, okay, and x1 is going to be equal to 0, and x2 is equal to 1,000. And you can see here that's how this negative number comes up, because you've got x2, which is greater than x1, and then you have h1, which is greater than h2. So you wind up with a positive in the numerator, a negative in the denominator. So you need this negative sign to make the flow work out. Okay, so for our example, our B will be 50 feet, and we'll say our width is equal to 1,000 feet. Okay, and so this is the simplest of the flow equations. It's going to seem pretty straightforward to you. Okay, and that seems like that would be our answer. However, people tend not to work within cubic feet. It's just harder. People don't generally have a feel for what the volume of a cubic foot is very easily, and it's usually we have like gallon buckets sitting around to measure flow. So we're going to convert that to gallons per minute. So we've got 1 cubic foot is 7.48 gallons, and then there's 60 seconds in a minute, and you do that, and that's 147.2 gallons per minute. Okay, and so that seems like a relatively straightforward bit of math, and it helps us estimate flow. And so if we happen to have a situation where you know what the water elevation is over here, and you know what the water elevation is over here, based on the material property and the distance between those 2 points, and of course the aquifer height and the aquifer width, then you can make some estimation for the amount of flow right here. And so seems relatively straightforward, and this is the basis for all of our groundwater work. Now, as we progress through this, you'll see that things are not always that simple, but in our next step, we're going to put this into a computer model and see if we can get the same result. And when you look at this, you might say, well, that's pretty easy, but as you progress, you might see that there's actually more complicated problems, and so it would be useful to be able to run a computer model.